Alright, welcome to the first section in chapter 13 where we're going to be talking about vector functions and space curves. So far in this class we've pretty much just gone over the three-dimensional coordinate system, how to write lines, and basically how the three-dimensional coordinate system looks in terms of just how everything's working in space as opposed to just a two-dimensional coordinate plane. So the first part we looked at, understanding how things are going to look in 3D space, and now we're actually getting to some of the calculus in this course. And so the first thing that we're going to talk about is a vectored value function. And a vectored value function, or a vector function, is just a function whose domain is a set of real numbers and whose range is a set of vectors. So now what we're doing is, and I'll explain a little bit more about this on page 2, we are now going to be able to define what our curve looks like through space. And in order to, write out what the curve looks like, it's going to be given as a vectored function. So a vectored function basically is just an extension of parametric equations. Notice for our vector function r of t, alright, it's just sine of t, cosine of t. Well, that's just an extension of parametric equations because our x component is just sine of t, and our y component is cosine of t, and our z component is just t. And so what we have here is just, when we look at vectored functions, we're just thinking, oh, these are just, parametric equations that are describing how, our curve, not a line, but our curve looks through space. Alright, so we could just write this as r of t is equal to a function of t, functions of t and g, and h of t, where they each represent, a different type of function for each component, x, y, and z. We use the letter t to denote the independent variable because it represents time in most applications of vector functions. So let's look at example 1. All we're going to do is we're going to find the domain of our vector function. And so we have r of t. And so what we have is we have our component for x is going to be defined by this function, the square root of t squared minus 9 over t minus 4. And because we want to determine the domain of our entire vector, we need to determine the domain of each component. And so the domain of the first, I put equal sign. What is x not allowed to be? Well, if we look at the denominator, t minus 4, we know that the denominator cannot be 0, so t does not equal 4. In the numerator, we have a square root, and we know that we're not allowed to have any negative underneath the square root. Because we're not allowed to have any negative underneath the square root, we could factor t squared minus 9. If we factor t squared minus 9, it would look like this: t minus 3 and t plus 3. All right, we could factor it, and that tells us, okay, we're going to have important parts that are going to end up at 3 because that's going to give us 0. For this, let's go ahead and get rid of all that. That tells us that our domain is either going to be values in between positive 3 and negative 3, or values outside of negative 3 and positive 3. And because it's t squared minus 9, the values that we're able to be are going to be t is less than or equal to negative 3, and t is greater than or equal to positive 3. Any values in between those are going to give us, a negative value. So if we try it, and again, you can try this, plug in 1 squared minus 9, and of course it's going to be a negative value. So that's our domain for the first component. Our second component is y, and that function is 2t plus 4. And again, because we have the natural log, we can't take the natural log of a negative value or 0. And so that means that where our domain is defined by t is greater than -2. And lastly, we have z, and we want to determine the domain of t, and it's a sine of t, and that's just going to be all real numbers. There's no restriction on our variable t there. And so now we're finished. What we're going to do is we're going to take, kind of the most restrictive parts. And so we have t does not equal 4, t is less than or equal to -3, and t is greater than 3, t is greater than -2, and all real numbers. So what we're going to do is, for t is greater than -2, we know that we can't be any value less than -2, so that's going to rule this part out. And because t is greater than or equal to 3, that rules that out. And so everything that is now it's been ruled out, I'm going to take it into account. So my domain is just going to be 3 to 4 and 4 to infinity. And again, so taking the domain is not bad. It's just you're taking the domain of there are 3 components, those 3 different functions, and you're taking out all the restrictions and putting them to where they all fit into the same domain. Alright, so next, definition. The limit of a vector function r is defined by taking the limits of its component functions as follows. So just like the domain, if I want to take the limit of a vector function, I'm just going to take the limit of each component of my vector function. And so we're going to do the first. We're going to find the limit of the first component, second component, and then third component. So the limit as t goes to 1 for t squared minus t over t minus 1. And again, you can always plug in to see what we get, but if we plugged in here, we're going to get 0 over 0. Because we get 0 over 0, I'll see if I can change the way this looks, and I can rewrite this as the limit as t goes to 1, pull out a t in the numerator, t minus 1 over t minus 1. T minus 1s will cancel out, and so I'm left with the limit as t approaches 1 of t, substituting that for that. And so the limit of that function as t approaches 1 is just going to be 1. Alright, now to find the limit of the second, we have the second component, the limit as t approaches 1, square root of t plus 8. Again, the first thing you do, substitute it in. 1 plus 8 is 9, so we're dealing with the square root of 9. And so the square root of 9 is just 3. So again, that one's fun because it's not very difficult. But the last one, we have the limit as t approaches 1, sine of pi t is less than the natural log of t. Now, if we substitute in for this, 1, we're going to get sine of pi, which is 0, and natural log of 1, which is 0. So we get 0 over 0. Because we do that, we know that we can go further, and so what I'm going to do is L'Hopital's rule. Spelled that wrong. L'Hopital's rule. And in doing L'Hopital's rule, we're just going to take the derivative of the top and then take the derivative, make sure I don't spell that wrong, the derivative of the denominator, and then plug in my limit once again. So the derivative of sine of pi t is just pi cosine pi t, and the derivative of the denominator is just going to be 1 over t. And we're going to substitute in our 1. So we get cosine of pi, pi times cosine of pi in the numerator. That's going to give us a negative pi. And in the denominator, whenever 1 is just 1, so then our limit is just negative pi. And so that tells us that, our limit for our vector function in question 4 is just going to be, since it's in terms of standard basis ijk, we're going to write this as I from 1 plus 3k, plus 3j minus pi